Hi, welcome back. In this video we're going to consider the process of translating a ER design, and in fact the ER design that we did on the Lightboard a few videos ago, into a schema in the SQL data definition language. So basically this is taking a design and converting it into something implementable. Alright, so here's the schema that we looked at earlier, or that I designed earlier. 3 entities, beers, bars and drinkers, relationships between them, all end-to-end relationships, primary keys. Each entity has a primary key called name, slightly unusual. One of the relationships also has an associated entity price. So bars sell beers. A bar sells a particular beer at a particular price, so that's what we're representing there. Okay, so let's get started. When you're translating an ER design, I guess one of the first things that you consider is how are you going to translate the entities. And of course, we looked at how to do that in an earlier video, just simply mapping ER entities and attributes into relational schemas. So we want to create a table corresponding to the beers entity, and most likely we also want to create a table corresponding to the bars entity. So I'll just start these off and we'll fill them in as we go. And we also want to create a table related to the drinkers entity. Okay, so that's a start. All right, one thing that we can say straight up is that beers has 2 attributes, name and manufacturer, and the manufacturer, and the name is the primary key. So in fact, straight away we could put primary key and assume that we're going to have an attribute called name. Now fortunately, name isn't a reserved word in SQL, so we can certainly use that for the name of an attribute. Okay, so the name attribute is going to be a string of text. How long should the name of a beer be? Well, these kind of questions plague database designers. Some beers have quite long names, so let's, for the sake of argument, we're going to allow beer names to be variable length strings, maybe up to 100 characters. Sounds kind of plausible. So we'll do that. And the manufacturer, similarly, is the name of the manufacturer, so it's also going to be a text string. Let's make it, let's say, beer manufacturers, i.e. brewers' names, aren't quite as long, so we can make that just up to 80 characters. Okay. Similar kind of deal for bars, so we've got a name which is going to be, let's make it the same. It doesn't have to be, we could make it 200 if we thought bars had particularly long names, but 100 sounds like a reasonable value. Okay, so what else have we got? We've got an address for each bar. Now addresses, given that they're just strings containing street, suburb, blah, 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 are actually likely to be quite a bit longer. So let's allow for 200 characters. And also, we've got a license number. Now you can see that the attribute in the ER design has a hash in it. If we really wanted to, we could include a hash in the name of the attribute, but I think it would be simpler just to use characters. And if you've got multi-word names in SQL, it's probably a good idea to use underscores to separate the words rather than try and do camel case, the uppercase letter at the start of each word, because Postgres maps everything into lowercase internally, and when you start looking at table names internally, the camel case goes away. So the license number, let's say license numbers have a particular format, and they're always 10 characters long, so we could actually define them like that. All right, a couple of other things to notice. We are currently allowing a bar to have no address and no license number. They have to have a name because name is the primary key attribute, and therefore name must have a non-null value. Similarly, we're allowing beers to have no brewer, or a brewer that we don't know. Probably a more realistic thing to do would be to insist that all of these other attributes, apart from the primary key, must be not null. So if we have a bar in our database, we have to know where it's located, and definitely we have to know its license number. So it makes sense to set all those to be not null. If you want, you could say that the name attributes were not null as well, but that's redundant because it's implied by the primary key. Right, the drinkers table is kind of similar to these, so I might just grab the text from here, save a bit of typing. So the name of a drinker, well, maybe drinkers' names aren't quite as long, so let's say that drinkers are going to have names that are 60 characters in length. We still have addresses. Okay, we'll allow them to be 200 characters long for the same reason as we allowed 200 characters for bar addresses. Drinkers don't have a license number, but they do have a phone number, and phone numbers tend to be roughly 10 characters long, but variable length, because you might want to include area codes, it might be a mobile number, and so on. So let's allow, say, 15 characters for a phone number. That seems reasonable. Okay, so these are the mappings for all of the attributes and entities. So now let's consider the relationships, and I might actually scroll that up and start looking at the relationship. So each relationship, as I mentioned before, is an end-to-end relationship, so it's going to be implemented by a separate table. So the likes relationship is an end-to-end relationship between a drinker and a beer, and so it's likely to have two attributes. Now, this is where we have to be a little bit careful. We have to make sure that the length of the beer name in the likes table is the same length as the name in the beers table. If we made it shorter, then there might be beers in the beers table that we couldn't represent in the likes table. So a little bit careful. And of course, I've now forgotten what the length was. Let's, for the sake of argument, assume that it's 80. We also need drinker, a drinker name. Once again, the size of the name string has to correspond to the one up above. I'm pretty sure I set drinkers to be 60. Do we have a key in this table? Well, yes we do. In theory we could set the primary key to be the combination of beer and drinker. In other words, we can say that John likes twoies. There's no point saying again that John likes twoies. So the combination of beer and drinker should be unique, which is what that primary key will do. Notice that we'll also, since those two attributes are part of a primary key, there's also an implied not null. Alright, so that's the likes table. We'll have a look at the frequent table, which is a relationship between a drinker and a bar, and it's very similar to what we had up here, which means that I'm going to steal the text and paste it in down here. In this case, rather than being a relationship between a beer and a drinker, it's a relationship between a bar and a drinker. And I'm pretty sure I made bars as varchar 100. Okay, and bar. So once again, if we say that John frequents the Coogee Bay Hotel, we have one tuple that says that. There's no point having another tuple that says the same thing, so the combination of those two attributes would make sense as a primary key. Final table is the cells table, which is a relationship between beers and bars. So let's define that table, create table cells. So it involves a beer, and we know that beers have names of length up to 80. We know that bars have names length up to 100, and the combination of those two is the primary key once again. But now we have something additional. We actually have an attribute, price, which indicates how much a particular beer is sold at a particular bar. So we can add an extra attribute. And this time, let's, just to be different, let's make it a floating point number, which looks to be a data type in PostgreSQL. Also, if we want to make sure that every beer has a price, we can insist that that be not null. Now, there's one thing that I haven't done yet. All of these attributes in these tables are actually foreign keys referring to an attribute in another table. So the beer references the name attribute in the beers table. Similarly, the drinker references the name attribute in the drinkers table. The bar references the name attribute in the bars table, and so on and so on. So to be precise, we really should put these foreign key indicators against all of the attributes in these tables. I won't do that because I know that some of them are going to overflow and make the text a little bit ugly. Okay, so that's it. We've taken the ER design and we've mapped it into a relational schema.